Okay, grade 11. So we're going to continue our end of chapter examples, and we're continuing with number 8. And number 8 is, you can see there that we have a graph. Okay, and the graph, Tony and Mark have done this experiment to investigate the laws of friction. Okay, and they've plotted force in newtons and the normal force. Okay, so the first question says, state the relationship between the friction, which is F, and the normal force as indicated by the graph. Okay, so question 8a. Remember, we always plot saying what the relationship is between the y versus the x. So I will therefore say that the frictional force is directly proportional to the normal force, directly proportional to the normal force. Okay, and let's just get that in a little bit here so you can see that nice and clear. And then we go to 8b, and in 8b they want us to calculate the gradient of the graph. So to work out the gradient of the graph, you can take, and they say of each graph. So what we do is we take 2 points on the graph and we can calculate the gradient. So for graph A, I'm going to take my 2 points as 0 and 0, and I would take my next point as 5 for my x value and 3 for my y value. Okay, so if I work out m now, which is the gradient, it's change in y over change in x. So I'm going to get 3 minus 0 over 5 minus 0, and I get my graph to be equal to 0, 6. Gradient of the graph to be 0, 6. For graph B, I get 0, 0 again. And another point that I can take that's very clear on graph B is I can take 5 and 2, 5. Okay, I just want to show you that this point, the 5 and the 2, 5 is what I'm using for graph B. All right, again, we work out the gradient. M is equal to delta y over delta x, and that will equal to 2, 5 minus 0 divided by 5 minus 0, and the gradient of that gives me 0, 5. So we're done with B. Let's go on to C. Okay, C says, what physical quantity is represented by the gradient of the graph? Now, lots of you have issues with this sort of question. Now, if I look at the question, if you want to know what's represented by the gradient, look at what you're dividing by. I'm dividing the friction by the normal force. Okay, because my friction represents my y values and the normal force values represent my x values. Then go and have a look at any equation that you know that relates friction and normal. And you will find that you know this equation. Friction is equal to mu times n. If I make mu the subject of the formula, F over n is equal to mu. Now, can you see that this is what or how I calculated my gradient? So that would mean that the gradient represents the coefficient of friction, because we have calculated mu. Okay, the next question, D. Which graph shows the results for static friction, and give a reason for your answer? So remember, we always said that static friction is always greater than kinetic friction. So look at the gradient of your graphs. Can you see that you have a steeper gradient for graph A? Okay, so graph A will be the graph for static friction, and your reasoning can be, since F of S, that static friction, is greater than kinetic friction. Okay, we shall now proceed to the next example, and the next example is number 9, and number 9 has a 10 kilogram object. So there's your 10 kilogram object, and this object is accelerating. So let's just fill in there that this is the 10 kilogram object. And what we can see is that it's accelerating. Acceleration is equal to 5 meters per second squared. And this is at an angle, so it's being pulled at an angle of 30 degrees. And you are required to calculate the pulling force, which would be this force here, as is labeled in your diagram. Okay, so the object is resting on moving on a frictionless surface, so we don't need to worry about friction. Okay, so if we have a look at this this diagram, we can first find out. So if we look at the horizontal component here, and we look at the vertical component here, remember this is FH and this is FV. Okay, and we know the equation, the equation F resultant is equal to MA. Now, if you look at this object, it has one force acting on it. The only force it has is the pulling force. And that pulling force has the two components. So the resultant horizontal force is H, and that is equal to 10 times 5. So my horizontal component is 50 newtons. Okay, so if there was friction, then we'd need to take friction into consideration. But there is no friction here, so we can work out our horizontal component quite easily. Now to do my pulling force, I'm going to say the pulling force F is equal to F cos theta. Okay, now the horizontal component is equal to the pulling force cos theta. So the horizontal component is 50, is equal to the pulling force we don't know, and it will be cos of 30 degrees. So we solve for our pulling force, and we get our pulling force equal to 57,7 newtons, which is this force here. So the clear thing for you to have seen is that this horizontal component is the net force that's acting on this object horizontally. Very important, and that's a key question. Okay, we now move on to number 10. So with number 10, the question is, a cricket ball is thrown vertically upwards. So you got the ball and it's thrown vertically upwards. State the velocity at its highest point. So when this ball moves, it'll go up and it'll come back down. At the highest point here, what will the velocity be? The velocity is equal to 0 meters per second. Because when you throw a ball up, it has to go up, slow down, stop, and then come back to the original point, come back to Earth. Okay, And then it says state the acceleration of the ball at its highest point. So at this point here, when the velocity is 0, please remember that your acceleration is not equal to 0. Because acceleration means three things. It means speeding up, it means slowing down, or it means changing direction. And at this point, the ball is about to change direction. So it has an acceleration that's directed downwards, and that acceleration is gravitational acceleration of 9,8 meters per second squared downwards. So please remember that although the velocity is 0, the acceleration is 9,8 meters per second squared downwards. Okay, that takes up to number 10. We're now going to do number 11. Okay, so when we go up to number 11, it says it's a rocket question, and you can read the information. So this rocket has got a mass 40 kilograms. It's fired vertically upwards from the surface of the earth, and it has a frictional force and an upward force. And you asked to draw the free body diagram of the rocket. So when I draw the free body diagram, again, remember you start your free body diagram with the dot. The first thing that you would draw is the weight of the rocket acting downwards. And that weight, if you know the value, you also fill it in. 40 times 9,8, which is 392 newtons. Okay, the rocket is moving upwards, so it's going to have a much bigger upward thrust, like this here. And they gave us that thrust. They said that that thrust is equal to 600 newtons. Okay, the other force that this rocket is experiencing is friction. So because it's moving upwards, okay, then the friction is going to act downwards, and that frictional force there, so that's your friction, and your friction force is equal to 100 newtons. So that would be your free body diagram for your rocket. Okay, question B says calculate the acceleration of the rocket. Okay, again here remember we're going to use F resultant is equal to ma. That's very important. That's Newton's second law. So if we look at this free body diagram, we can see that the resultant force is going to act upwards. Okay, so for my resultant, I must have T minus, these two are vector quantities that are acting in the same direction, weight plus my frictional force is equal to ma. Okay, and the tension, the thrust, we know is 600. So it's 600 minus, we even know the weight, which is 392. When I open brackets, my friction also becomes negative, and I know that is 100, and that would equal to 40, which is the mass, and we don't know the acceleration. Okay, and we have an acceleration equal to 2,7 meters per second squared up. There we go. Okay, now we go on to question number 12. So for question 12, let's read the question, and it says that we have a lift that is descending towards the ground and it's slowing down. Draw a label free body diagram of the lift described your arrows must be drawn to represent the relative size of the forces. Okay, so if we look at the free body diagram for the lift, okay, it says that the lift is moving downwards and it's slowing down. So that means that the acceleration would be upwards. Okay? And because acceleration is positive or in the forward direction, if an object is going in the positive direction and speeding up, or if it's going in the positive direction and slowing down. Okay? So that means the upward force, which is the tension in the cable, must be greater than the downward force, which is the weight of the lift. Okay, in that way, this object will have a resultant force acting upwards, and the object will accelerate in the direction of the upward force. Okay, the next question is question number 13. Question number 13 says, let's just get that a bit there. Okay, so question 13 says, to determine the tension in a lift cable during acceleration, a man with a mass of 70 kilograms makes use of a spring balance. So we got a man. Okay, let's just extract the information. His mass is equal to 70 kilograms. Okay, then you have a spring scale. Okay, this is a lift example, and the spring scale has a mass of 0.5 kilograms. And the lift is accelerating upwards. The man records a reading of 8 newtons. So the reading on the scale, okay, is the reading on the scale TS is equal to 8 newtons. If the mass of the empty lift cage, so the lift by itself, has a mass equal to 1,000 kilograms. What are we required to calculate? We are required to calculate the tension in the string, okay, in the cable of the lift. That's what we have to do. Okay, so this is number 13. So the acceleration is upwards. Acting downwards, we have got the weight. So we go F resultant. Let's just put that there. F resultant is equal to MA. So it's the reading on the scale minus the weight is equal to MA. 8 minus, that's the reading on the scale. So if I work out the mass of the scale, the weight of the scale here, by saying 0.5 times 9.8, that's where I'm going to get 4.9 newtons for the weight on the scale. So that's going to be 4.9 is equal to mass, which is 0.5. I don't know what the acceleration is, but I can solve for the acceleration, which is 6.2 meters per second squared. Okay, I needed to find the acceleration so I can then find the tension in the cable. Okay, so now so the acceleration for the lift is also 6 meters per second squared, because remember, all the objects inside the lift will have the same acceleration. Okay, now we use F resultant again. F resultant is equal to MA. So it's T minus W now is equal to MA, and T minus the weight, okay, which would be all of the object's masses added. So the 1000 plus the 70 plus the 0,5, and I multiply that by 9,8 is equal to all of that and from there I get my tension equal to 16914 newtons. Okay, so these bits are important, especially adding all the masses, adding all masses. Okay, and when we so adding all the masses, you would see that the answer in your book is slightly different. It's because I think the values were carried on in the calculator, and also because we use 10 instead of 9.8 for that calculation. Okay, so don't stress too much about that. So now we on question number 14, and question number 14 speaks about the bee, a bee colliding head on with the windscreen of a car traveling at 100 kilometers per hour. Compare the size of the force exerted by the car on the bee with the force exerted by the bee on the car, and give a reason for your answer. So remember now, B on car, car on B, the forces will be the same in magnitude but opposite in direction. Okay? Same in magnitude but opposite in direction. That's because of Newton's third law. Newton's third law. Remember, the key aspects in Newton's third law is that it's the same two objects. Okay, obviously the forces are equal but opposite, and they act simultaneously. That means at the same time, not 2 minutes later. Okay, then we go to question number 15. Okay, and question number 15 is about Megan and Peter, and they're having a tug of war, and you need to draw a free body diagram showing all the forces acting on Megan. Okay, so firstly, when we draw the free body diagram, remember Megan is on a surface, so Megan's going to have her weight acting downwards. The surface is also going to have the same size, normal force exerting upwards, and then we're going to have the rope on Megan. So this rope here on Megan, because remember Peter is pulling. Rope on Megan, and the other force will be a little bit of friction. Okay, so that's the free body diagram. Then it says according, oh, I should have made actually this much bigger. Just hang on a second, because acting on Megan. According to Newton 3, the force which Megan exerts on Peter is the same in magnitude as the force which Peter exerts on Megan. Explain how Megan can win. Okay, so you can see here that the person that's winning is Megan, because Megan is moving backwards. Starts moving backwards. Because if she was moving forwards, then that would mean that Peter was pulling her. So when she starts moving backwards, she starts to win. Okay? But there is a resultant force. Okay? So there is a resultant force that's acting on her in that direction. So then the frictional force of the ground on Joshua, on Megan,